first recall what we have studied. In the last class, in the last lecture, we have studied energy bands in solids. So, energy bands in solids. And therefore, in general, solids are characterized by energy bands. The highest band, which is completely full or nearly full, is called the valence band, and the next band, the next higher band, is the conduction band. Conduction band. It does not mean these are the only two bands. There are many more bands which are below, but the electrons in those bands rarely participate in any of the electronic processes unless you use high energy X-rays to knock them off. So, normally the electrons which participate in optical and electronic processes are those in the valence band and the conduction band. Therefore, if I draw the band diagram, which you have seen in almost all books, metals, semiconductors and insulators are basically characterized by band diagrams. So, let me draw the band diagram. Although I am plotting the bands at the same energy level, so this axis in all through the course, the vertical axis will be energy. In metals, we have either a completely full valence band and almost half filled conduction band. This is conduction band, this is valence band. If it is almost half full, it means rest of the half is empty, or there are free states which are available for occupation. There are filled states and free states, and we have already seen the typical number of electrons is of the order of 10 to the power of 22 per cc, which means very large number of electrons present and large number of free states present, which will facilitate movement of electrons in the presence of an external applied electric field, and that leads to very good conductivity of the material. It could be like this, or it could be overlapping bands. In some cases, the conduction band and valence band overlaps, and then also you have large number of electrons and large number of vacant states in the same band, and therefore electrons can move very easily. In the case of semiconductor, at 0K, valence band is completely full and the conduction band is completely empty. Typically, the band gap here, Eg, now we talk of band gap Eg because electrons have to go up. Eg is of the order of 1 electron volt. As I mentioned, that anywhere from 0.1 electron to 3 electron volts is the band gap of semiconductors, but let us say 1 electron volt. At any finite temperature, a finite temperature T, there are electrons which go to the conduction band, which lead to conductivity. The electrons can then, if some electrons come here, then there are free states, vacant states, and the electrons can start moving through the band in the presence of an applied electric field. The electrons which go here leave behind holes which are nothing but vacancies in the valence band. Holes exist only in the valence band and not in the conduction band. The vacant states in conduction band are different from the vacant states here. These are holes which are vacancies created in an otherwise filled valence band. In the case of insulators, the band gap here, energy gap is very large. I have shown them all at the same level, but please see that these gaps are different for the 3 different materials. So, what I have drawn is energy bands in solids. So, metal, semiconductor, and insulator. Because the electrons in the conduction band have gone up or have made an upward transition from the valence band, naturally the number of electrons present at any temperature is given by, depends on the gap. Smaller the gap, larger will be the number of electrons which can make an upward transition, and larger the gap, smaller will be the number. In general, when Eg is greater than or of the order of 3 electron volt, 4, 5, 6 and all, then the number of electrons which can make an upward transition becomes extremely small, and therefore the conductivity of such materials is very low, and these are nothing but the insulators. So, from the band energy bands in solids, we generally characterize metals, semiconductors, insulators in terms of this energy band diagram. But these energy band diagrams do not tell anything more beyond this. So, to know more optical and electrical properties of a semiconductor or any material, you have to go to the EK diagram, which is called the band structure. So, EK diagram. It is the EK diagram which will tell you many more things. So, let us discuss the EK diagram, or this is called the band structure. The band structure. Just before I go over there, you know that at room temperature, let's say around at room temperature, so T is equal to 300 K. We have, let me take silicon, germanium, let me take 3 semiconductors, germanium, silicon and gallium arsenide. The energy band gap is 0.67 eV. For silicon it is 1.1 eV, 1.1 eV. Gallium arsenide has a band gap of 1.42 eV. Which means if this band gap is about 1 electron volt, then an electron which wants to make an upward transition here must have energy of the order of 1 eV or more. But in general we know that the energy of electrons, average kinetic energy of electrons, E, is of the order of kT at a temperature T, where K is the Boltzmann constant. So, this is 1.38 into 10 to the power of minus 23 into, let us say, 300 divided by 1.6 into 10 to the power of minus 19 eV, and that is approximately equal to 0.025 eV. We are familiar with this, average kinetic energy of electrons. How is it that when the kinetic energy is, or when the energy of the electrons is of the order of this, how is it that the electron is able to make an upward transition? Think over this. You know that at room temperature, germanium has typically of the order of 10 to the power of 13 electrons per cc. Silicon, this is not doped, this is intrinsic pure material. The intrinsic carrier concentration due to temperature is of the order of 10 to the power of 10 per cc. 10 to the power of 10 per cc. And for gallium arsenide, it is of the order of 10 to the power of 6 per cc. How is it that so many electrons make an upward transition at room temperature? At 0 K, in a semiconductor, the valence band is full and the conduction band is empty. How is it that such large number of electrons exist in the conduction band at room temperature. Give a thought about this, then we will discuss further. So, let me go further to discuss the EK diagram, energy versus K. In the last class, we discussed that most of the useful semiconductors are crystalline, and in crystalline semiconductors, atoms are arranged periodically in a lattice. The periodical arrangement, if I take a 1D arrangement for simplicity, periodical arrangement leads to a periodical potential variation, periodical variation of potential energy here. But the motion of electrons in a crystal is governed by the laws of quantum mechanics. If you have one electron, one proton system like the hydrogen atom, it is very easy to solve the Schrodinger equation. But in a solid, when there are large number of electrons and atoms present, it is extremely complicated and difficult to solve the Schrodinger equation. But F block, I am sure you have heard of Bloch. Bloch observed that his observation was, since the potential varies periodically, the probability of finding an electron should also vary periodically. Remember, the probability of finding an electron should also vary periodically, which means the wave function should also vary periodically. Please see, probability of finding an electron is equal to mod psi square, where psi is the wave function. And therefore, he postulated that in such periodic medium, the wave function should be of the form psi k of r is equal to uk of r into e to the power I k dot. That is, the wave function is a product of a plane wave. This is a plane wave. E to the power of I k dot r is a plane wave, and multiplied by a periodic function which is called the cell function. uk of r is periodic. uk of r plus a is equal to uk of, sometimes I write, is the same k. Sometimes I would have written like this, sometimes I write like this. Please, although I should have been careful. So, I k dot r. So, this is a periodic cell function. This is a periodic function where A is the interatomic spacing. So, he postulated that the wave function must be of this form, a plane wave multiplied by a periodic function. If you substitute this form of the wave function in the Schrodinger equation, del square psi plus 2m by h cross square into E minus B into psi equal to 0, then it turns out that this can be solved by several numerical and analytical techniques. There are several methods by which you can solve this. If you substitute this form of psi in this, then you can solve these and you get energy values, eigenvalues. Please see here, E is the energy eigenvalue, V is this periodic potential, and m is the mass of the electron, psi is the wave function. So, you get energy eigenvalues. E also turns out to be periodic in K, which means if you plot I am directly giving you the results of this. If you plot energy versus K, E versus K, then for each allowed energy level, each allowed discrete energy level, you get periodic functions. So always the vertical axis is E and this axis is K, Ek. This is E versus K, which means for every given value of K, this is K is equal to pi by A, K is equal to 2 pi by A, K is equal to minus pi by A and minus 2 pi by A. Corresponding to every energy level of the single potential well, you have now a periodically varying energy value. If you see the first boundary here between minus pi by A and plus pi by A, which is called the first Brillouin zone, these are the borders of the first Brillouin zone, the first Brillouin zone. I will not go into the details and origins of Brillouin zone because this is in the reciprocal lattice. There are some important points, but what we are mainly focusing is on K is equal to 0, that is K, we will see shortly that Kx, Ky, Kz equal to 0, which corresponds to K equal to 0, and this is called the gamma point. If you have not come across these, you may go through, but we are not very, in this course we are not very much keen on the Brillouin zones, gamma point, X point, L point, there are different various points. But what I want to bring to your attention is that energy versus K is periodic because the potential is periodic. Since it is periodic, it is sufficient for us to restrict ourselves to one period, minus pi by A to plus pi by A. If we know the value from minus pi by A to plus pi by A, then we know everywhere because it is periodic. And therefore, in a reduced zone picture, in the Ek diagram, there are, so Ek diagram, there are 3 pictures. I am sure one of them will be the picture that you have seen. So the first one is periodic zone picture, periodic zone. The second one is called the reduced zone picture, reduced zone, reduced zone. And the third one is called the extended zone. Extended zone picture. There are 3 pictures for the Ek diagram. What I have plotted is the periodic zone picture. In the reduced zone picture, you simply reduce this up to the border of the first Brillouin zone, because you know that if you know up to this, you know beyond this. So this is the reduced zone picture. So normally when we see the EK diagram, we look at the reduced zone picture. These correspond to different levels. And if you see the reduced zone picture, and the highest field energy level is the valence band, and the next one is the conduction band. And if you look at these bands and draw the reduced zone picture, then we focus only on this part of the EK diagram, K versus E. Why are we focusing only on this part? I will tell you in a minute. Now let me complete what is this extended zone. In the extended zone picture, if you know up to this here, and then there is a, please see, this would have gone like this. So in the extended zone picture, you show this discontinuity and wipe this. So you have come up to, this is at pi by a, this is at 2 pi by a. And corresponding to the next band, you have a discontinuity and then again going like this. So this is the extended zone picture where you show from 0 to pi by a for one level, pi by a to 2 pi by a for the other level, corresponding to other level, and so on. So this is the extended zone picture which you normally plot from the Kronig-Penney model. From the result of the Kronig-Penney model, you will see that there is a discontinuity and then you see the extended zone picture. But here for this course on semiconductor optoelectronics, it is sufficient for us to see the reduced zone picture. And more importantly, it is even sufficient for us to focus only at the bottom of this and at the top of this. The top of this valence band and bottom of this conduction band, it is sufficient for us to focus on this. Why? I will tell you in a minute that when we calculate the density of states, which will be our next topic, we will see that the density of states in a band is extremely large, and the number of electrons or the carrier concentration which is responsible for the flow of current is extremely small, and only a small portion of this EK diagram, that is only the lowest portion of the conduction band, or only electrons which are holes which are close to the top of the valence band participate in all processes, all electronic processes. Therefore, it is not even, you rarely meet these ends, the ends of the Brillouin zone. All the practical devices, almost all the practical devices, utilize carriers which are close to the bottom of the valence band and close to the bottom of the conduction band and close to the top of the valence band. And therefore, if you see a simple device, a device oriented book, they will draw EK diagram only this much. Although the EK diagram continues. Let me plot that lowest portion of the EK diagram, the relevant portion of the EK diagram, and discuss further. So now we have the EK diagram. When you plot the EK diagram, so this is K, you could draw a K here also. Vertical axis is always E. So what does this represent? This represents, for every value of K, we will see shortly that the K values are discrete. For every value of K here, what is the corresponding allowed energy? That is a solution of the Schrodinger equation. So what you are plotting is allowed energy values as a function of K. we will see that the k values are discrete, but the number of values are so large that you plot a continuous curve. So, materials in which, there are materials in which the top of the valence band here coincides with the bottom of the conduction band, and there are materials in which the top of the valence band does not coincide with the minima of the conduction band. So, materials in which, so E versus K, materials in which the minima of the conduction band coincides with the top of the valence band, coincides means occurs at the same value of K, occurs at the same value of K, are called direct band gap semiconductors. And materials in which the minima of the conduction band EC is denoted by EC, EV. So, this value here is EC, the band edge EV, coincide, does not coincide, are called indirect band gap semiconductors. So, two things to note, that K can take large number of values. What is this K? We will see shortly. Again we will recall what is this K. And corresponding to each K value there is an allowed energy value. Allowed energy means an allowed solution of the Schrodinger equation, and we plot energy versus K, and that is the EK diagram. Also please recall that we had drawn an energy band diagram, the familiar energy band diagram, where you show that, okay, this is the valence band and this is the conduction band. So, this is the conduction band and this is the valence band. This is the band edge, which is EV, and this is EC. Have the clear picture that this EC is the same as this. The bottom of the EK diagram here, the bottom of this here EC is the same as this, and the top, the band edge here is the same as this. And this was going up and then turning like this. So, the maximum allowed value was this, and this was going down and turning like this. So, the minimum energy value is this. So, the point is the basic energy band diagram which we have studied in basic classes is exactly, it corresponds to the EK diagram. But this does not tell anything further other than the band gap. But you will see that it is the EK diagram which will tell us more about the optical and electrical properties of the material. So, this is 1-to-1. Usually the holes which are close to the top of the valence band and the electrons which are close to the bottom of the conduction band participate in all the electronic transition processes. And that is why I had mentioned that it is only the top of this and the bottom of this which are in practice relevant to the optical and electrical properties. I proceed a little bit further to see what is this K. This K is the propagation vector of the electron wave function, is the propagation vector whose magnitude K is the propagation vector. Whose magnitude is given by 2 pi by lambda, where lambda is the de Broglie wavelength, of the electrons in the medium, in the semiconductor. This k is such that the momentum P is given by h cross k. The momentum P of electrons in the semiconductor is given by h cross k. This momentum is very often called the crystal momentum. The crystal momentum. Please see an important concept here. This comes from, you are familiar with the de Broglie wavelength, lambda is equal to h by p. Lambda is equal to h by p, where h is the Planck's constant and p is the momentum, or p is equal to h by lambda. So if you divide and multiply by 2 pi, this is nothing but h cross k. So momentum is nothing but h cross k. Momentum is a vector, therefore this is h cross k. And this is how you get this. Now this is called the crystal momentum. See this picture. If you take a semiconductor, there are large number of atoms and electrons, the ions and the electrons. Any electron here, any electron E is moving through this medium under the influence. When there are positively charged nuclei and negatively charged electrons, there is an electrostatic field. So any electron which is moving through this moves under the influence of an electrostatic field which is inside the crystal. This is called the crystal field. This is a crystal field, internal field. Electron is moving through it. It is not moving through free space, but it is moving through the medium, and there are large, a very complex crystal field which is present. If you apply an electric field to this, you apply an electric field, so the electron starts moving. This is an external electric field, so you have now applied an external electric field. Please see, there is an internal electric field. The electron has to move in the presence of an internal field and an external field. So the force, the net force on this, on the electron, net force on the electron will be due to F external plus due to F internal. F external is because of the applied electric field, which means you know that it is minus E into E. This is the external field. I applied an electric field out from outside, which means there is a electric field E. So the force is charge into E, so minus E into E. What is the internal field? It's really very complicated. If you define the momentum by this expression, where this K is the same K which appears here, psi K of R into UK of R into e to the power of I K dot R. It is the same K which is the de Broglie wavelength, 2 pi by lambda. If you define that, then this is called the crystal momentum, which means this momentum is as if it is responding only to the external field. In other words, you have dP by dt. What is this? rate of change of momentum is equal to F external. Normally, that if P was the total momentum, it should have been, F must have been equal to dP by dt, force equal to rate of change of momentum. But if you define P by h cross k, which is called the crystal momentum, then the crystal momentum is responding only to the external force, and you can write this equation dP by dt is equal to F external. This F external we know, because this is very important. What you know is E, you don't know the internal field, and therefore it is as if the electron is responding to the external force as if it is a free particle. Please see this. And then it moves with the mass which is equal to the effective mass of the electron. The effective mass, which is defined by 1 over h cross square d square E by dk square to the power minus 1. I have actually skipped the derivation of this. There is a very complex derivation and also there is a simple heuristic derivation. Both I have skipped at this moment, but what I would like you to appreciate is this, that if I define the electron mass by this effective mass of electron, effective mass, it is as if this is an electron, it's a free electron which is directly responding to the external force, which is directly responding to the, when we write F is equal to ma, this is the mass of the particle and this is its acceleration. This is for a free particle. F is equal to ma. So if you define an effective mass for an electron which is given by d square E by 1 over h cross square into d square E by dk square to the power minus 1, then this electron inside a semiconductor can be treated as if it is a free electron moving under the influence of the field. You do not need to consider the internal forces within the semiconductor. It is as if the electron responds directly to the external force. That is why, now what you see here is this is d square E by dk square. Where do you get this from? I skipped the derivation, but to get d square E by dk square, you need the EK diagram. So you have the EK diagram here. So this is the EK, and the second derivative gives you d square E by dk square. And this is the effective mass. So it is the EK diagram which will tell you what is the effective mass. I want to give a few numbers of effective mass and why this is important. Why am I discussing all these? We are engineers, why all these details are required? Please see this. If you are a device engineer, usually the control parameter is I, the current. I is equal to J into A. J is the current density multiplied by area. If this is your device, you are applying an external field and then you want to see what is the current I. J drift, because of an applied field, so what you have is J drift is equal to N, the carrier concentration, charge multiplied by the mobility, E, into the electric field. Because of this, there is an electric field here, E. So the drift current density is equal to this, because we need this to know what is the current generated in this medium. So what are the things that you need to know? N, carrier concentration. carrier concentration. Carrier concentration in the conduction band is given by N is equal to N of E, that is at every given value of E N, this is carrier density into dE. If you are looking in the conduction band, it starts from EC to infinity. So this is carrier density. Why all these physics for engineers? That is the question. So engineers talk of current. Current is given by this. So this is the carrier density, N. N of E, the carrier density, N of E, please see the context of this discussion. N of E is equal to rho of E into F of E. Rho of E is the density of states, which will be our next topic, density of states. Almost every course you will come across density of states, whether it is optics, semiconductor physics, quantum mechanics, density of states multiplied by F of E. What is F of E? Probability of occupation. Probability of occupation. So density of states multiplied by the probability of occupation will give you carrier density, and integrate over the entire band, that will give you the carrier concentration. That carrier concentration you need to substitute here if you want to find out the drift current. What is Q? Q is the charge. This is the electric charge. Mu E is the mobility of electrons. Mu E is the mobility. This mobility is given by charge E into tau C divided by m star, where this is the effective mass. Mobility is given by charge E or Q, charge, multiplied by carrier recombination time divided by m star, where this is the effective mass. So we need to know effective mass to know the mobility. To know the effective mass, it is essential to know the EK diagram, the band structure. Only that will tell you what is this. So I will give you in the next class some values of mobility and effective mass in various semiconductors, and you will clearly see the smaller the effective mass, larger will be the mobility. So for a given applied electric field, you need to know mobility, which depends on m star. You need to know the carrier concentration, which depends on the density of states and the probability of occupation. So to know m star, you need to know the EK diagram. All right. We will see that EK diagram is also the one which will determine the optical absorption and emission processes. Radiative processes and non-radiative processes, their probability of occurrence is determined by the band structure, which is very important in optoelectronic devices. So I will stop at this point, and in the next class we will continue with the density of states and then probability of occupation, and then we will go over to semiconductor materials and then come to the interaction of electrons and holes in a semiconductor. Next class we will also have a quiz. At the end of the class I will give you a quiz question, and it is basically, it could be one word answer, one sentence answer, or a very small question. So just to keep a piece of paper ready, and write on that and give it to me, and then you can leave, right? Okay, thank you.